Now let's talk about the principle of superposition. In 우리말 it is called 중첩의 원리. 중첩의 원리. Actually, the principle of superposition underlines very important procedure in practice. We use the principle of superposition with the assumption of linear elastic behavior of my structural system. Let's consider one-dimensional system here. The first equation is the elongation of one-dimensional bar subjected to the internal force N here. Then here we can easily find that instead of elongation, we can put the nodal displacement. Instead of internal force, we can consider force F. And then here, the elastic modulus times the cross-section area divided by the length is equal to the stiffness. Then we can obtain the well-known spring equation. The spring modulus K, and then the end displacement is equal to the applied force F here. And this one-dimensional equation can be extended to the multi-dimensional version very easily. Now, instead of just one number of single stiffness, we have two-dimensional matrix. The stiffness, this is called the stiffness matrix. Stiffness matrix. And then here, instead of just single nodal displacement, we may have multiple nodal displacement. And then for the multiple degrees of freedom problems, we can set up this matrix equation. So the principle is exactly the same, okay? So let's consider I have a linear elastic system. So if you have a linear elastic system, so let's consider I have one linear elastic system. Here I have displacement and then force as a consequence. And then this is my behavior, my structure. And then its modulus can be measured by the spring modulus here. Let's say we want to consider U1, okay? For U1, then my structural response would produce F1 from my structure system. And then if you consider U2, and then its behavior is equal to F2. Then our question is, this is okay, U1, okay, and this is U2, okay. Then my question is, what's gonna happen? So if you consider U1 plus U2, okay, then this is the question. So let's take a look. So if you apply U1, then we can obtain F1. Then F1 is stiffness times U1. And how about U2? If you do that, then K is equal to F2. Then if you add these two equations together, then we can obtain F1 plus F2 is equal to the stiffness U1 plus U2. Okay, for U1 plus U2, we can get the response is what the sum of the responses from these two individual independent behavior. Okay, this is the principle of superposition. So which means if you have complicated load systems, for example, let's say I have distributed load and then concentrated load, instead of talking about handling these two different types of loads, we decompose these loads into two, the one distributed load and the one concentrated load. Then for the simple load cases, we get the solution. And then once we have the solutions, we superpose these two solutions together, whatever, for the stress or for displacement or the internal forces and whatever, okay? And this is another example. This is statically indeterminate structures here. Here, some of people are confused with the nature of the structure system. Even sometimes they consider the support condition as part of structure system, but it is not. My structural body is only the girdle, okay? And then the force caused by support system can be considered external load systems. So here, which means I have 1, 2, 3, 4 different loads, okay? 4 different loads equals 4 different loads. Then I want to consider one apparent external load, and then I want to consider the other the reaction force here. And of course here there must be reaction to the R1 for system B, the R2 for system B, here R1 for system C, and then R2 for system C. Because these two are statically determinate, and we can solve the structure system very easily. And then here, because of superposition, R1 is equal to R1B plus the R1C, isn't it, right? And how do you finish this solution? Here, make sure that here R is unknown. And then to solve this problem, if you look at the original structure system, here the vertical displacement at the point of support is equal to 0. So we superpose displacement measured here and the displacement measured here. Then we find out a reaction which cancel out displacement at this point, and that is the correct solution for this problem. Okay, so there is a handbook. Okay, there is a handbook for various design equations. For simple problems, that we can use handbook instead of solving problems. So let me check. Let me see example here. This is one of well-known design formulas. This is a ROAX formula for stress and strain. And then if you search this textbook, this design handbook on internet, this is free. Okay, this is open free to public. That's why you can download this PDF version of textbook for your use. And then, for example, let's go for beam problem, and then let me check here. And then here, if you open this textbook, and then there is content. And for these contents, we can find some information for fact and principle, the method, and the analytical method, and also numerical method. And then in part 3, so we can get various formulas and examples, and tension, and compression, shear, and combined stresses. And then for beam problems, now we are talking about beam problem here. So they provide various formulas for beam and flexor, straight bars, and then the straight beams, and then or the rigid frames, the beams on elastic foundation, and then they provide various formulas for this category. For example, let's move that place. For example, I check the advanced, and if you go here, you can find the various design formulas here in the form of table. So we can find the reactions and the maximum moment and the deflection for various conditions. Okay, so once we are able to simplify the problem or break down the problem into simple units, then we can take advantage of design formulas, so rather than solving the problems so manually. Is it clear, right? And that this is how to use a design formula. Okay, let's take a break.